6.2, the chain rule. We're going to work through the formal pieces in subsequent classes, but this is just kind of kick off the process. We're going to find the chain rule is one of the most important fundamental elements of calculus. And why is that? Well, the key thing is because most functions that we deal with really in calculus are pretty complex, not just some basic polynomials. There'll be things of the forms that you see down here. Sine squared of x squared plus 2. 3x squared plus 2x raised to the third power. The natural log of 3 sine x, or e raised to the negative 1/3 x squared power. And what you notice in all these is, hopefully, a composition of functions, one function stuck inside of another. And so when we look at the rate of change, the derivative of a composite function, we kind of need to consider a few things. And so let's talk about the middle function. That's a good one to work with. 3x squared plus 2x inside the parentheses, and then raised to the third power. Well, we have a couple things going on here when we think about how is f of x changing. Number one, it's kind of changing because whatever inside that parentheses is being cubed. So we can see a cubic activity that's taking place. But before we get to the stage of actually cubing and implementing the associated rate of change that goes with that, we also have something happening in here. 3x squared plus 2x. That is also growing. So as we need to consider the overall growth, the rate of change, I say growth, it could be decay, just let's use the term rate of change, it's being influenced by a couple of underlying factors. And that's what we're going to look at as we start here. And what we're going to do is we're going to take the 5 derivatives that we know, we're going to use the power rule, we're going to know what we know about the derivative of the sine, the cosine function, the derivative of e to the x, the derivative of ln x. And we're going to start with just kind of a basic little language rule that I'm going to start to use for us with the chain rule. Here is f of x following along the lines of the power rule. I've just used something. It could be any of the things that we've seen in parentheses before, but for the moment I'm just going to call it something. And when I take whatever this something is and raise it to the nth power, I'm going to tell you that the derivative of that intuitively is going to be the following. Well, n times something to the n minus 1, which looks just like the power rule. I freely admit that something looks a little bit odd there, but whatever happens to be raised to the power, we'd multiply by n, take that thing, and now raise it to the n minus 1 power. And then what we're going to consider to get the overall rate of change, again, remember this is a composite function, we're also going to take the derivative of something. So when you see times something prime here, that means the derivative of something. So again, we did some of these pieces in class, hopefully you saw it or whatever, but we're going to work through these fundamental structures. Let's talk about sine and cosine. F of x equals sine of something. Well, what's the derivative going to be? Well, remember the derivative of the sine function is the cosine function. So the derivative of sine of something is nothing more than cosine of something times, again, the derivative of something. I've written this as something prime. When I have f of x equals a cosine of something, my derivative, f prime of x, is going to be, well, remember, the derivative of cosine is negative sine of something, whatever happened to be in the parentheses, multiplied by the derivative of something. Again, we'll see more of these as we keep working. Here we go. 2 more. F of x equals e raised to the, quote, something power. F prime of x is going to be what? E to the something. Remember, e to the x is its own derivative. So, in this case, e to the whatever that something is, e to the something, times, again, something prime, the derivative of something. Last one, the ln of something. What's the derivative of that function? Well, it's, remember, the derivative of the ln of x is 1 over x. Well, there we go. Instead of 1 over x, I have 1 over something. It's whatever I was taking the ln of, multiplied by the derivative of something prime. So what, again, I hope you're seeing is kind of there's a layering that's here. Composite function, one function inside of another. You might hear the terms inner and outer. Lots of different ways to do it. I like to use this something language because I find it pretty helpful. Now, in general, what's that going to lead us to? And this is what we'll see formally, but take a look. If I have a function f of g of x, the derivative of a composite function of the form f of g of x is nothing more than, look at that, f prime, whatever the derivative is of something. So in other words, I take the f function, take its derivative, evaluate it at g of x, and then multiply it by what? Hey, there's my something. Look at that, g prime of x. That's the derivative of something. So again, I want you to just kind of get this informal language. We're going to use U substitutions. We're going to use Leibniz notation. That'll put this in kind of a little bit more of a pure mathematical concept. But if you can understand your 5 basic derivatives, the derivative of the power rule, the derivative of sine, the derivative of cosine, derivative of e to the x, derivative of ln the x, you'll be able to see some of these patterns pretty quickly.